Hello, ma'am. In this presentation, we are going to learn about Harvard architecture machines. So, without any further ado, let's start the presentation. In this presentation, the objectives being first, introduce ourselves with what actually Harvard architecture machines are, and discussing certain examples, which includes digital signal processor, also advantages, disadvantages of Harvard architecture machines, and finally, conclusion about Harvard architecture machines. So let's start with the introduction. Microcontrollers generally are of two types: one human and Harvard architecture. One human architecture consists of control unit, arithmetic logic unit, input-output, and registers. In one human architecture, which is used by many microcontrollers, memory space is on the same bus and thereby instructions and data intend to use the same memory. It is used the concept of stored program computer. Our architecture consists of arithmetic logic unit, data memory, input-output, instruction memory, and control unit. It has memory for data and instructions. In that way, both instructions and data can be fetched at the same time, thus making it comfortable for the users. It has separate memory for data and instructions. In that way, both instructions and data can be fetched at the same time. Moreover, in Harvard architecture, instructions are used in read-only memory and data are used in read-write memory. Harvard architecture is used with CPU mostly, but it is used with main memory at times as it is a little complex and on expensive side. The size of memory for both instructions and data are different in the case of Harvard architecture. Programs cannot ever run automatically and the organization of memory is not in the hands of the user. We can look at the various features of our architecture in this presentation, which will be discussed further. Let's go with an example to better understand Harvard architecture. One example of Harvard architecture is the early computer mainframe systems, where instructions are stored in one programming media such as punch cards and data are stored in other programming media such as tapes. The results of the Harvard architecture are their corresponding images. Data flow machines and reduction machines are examples of Harvard architecture as well. They exhibit a high rate of parallelism, meaning that the results from the data and instructions can be obtained at the same time. The following image illustrates about how data and instructions are on separate memory. Quantum computers can also be cited as an example of Harvard architecture. The difference between other computers and quantum computers is that they require to complete a task and the order in which they prioritize their timings. Enigma machines, which were used in World Wars, are also follow the Harvard architecture. Yet another main example of Harvard architecture is digital signal processor, which is primarily dependent on the concept of Harvard architecture. Now let's talk about certain facts of Harvard architecture which are fascinating. The first being Harvard architecture speeds up the processor rate. It is because data and instructions are stored in separate buses and it is advantageous for the user. Also, Harvard architecture follows a pipeline arrangement. In this arrangement, execution of one instruction goes on and the other instruction is fetched from the memory simultaneously. This allows overlapping of instructions and the execution rate is increased considerably. RISC, that is Reduced Instruction Set Computer, and CISC, Complex Instruction Set Computers, are the methodologies used in Harvard architecture. The RISC microcontroller data is 8 bits, whereas instructions as 12 bits or 16 bits wide. Thus, everything is executed at a time, resulting in increased performance. In CISC, both data and instructions are 8-bit wide and they generally have over 200 instructions, but they cannot be executed at a time rather fetched simultaneously. Now, the execution unit consists of mainly two arithmetic and logic units, one being shifter, one being multiplier, accumulator, and so on. Thus, they execute arithmetic operations in a stable way with excellent parallelism. That is, arithmetic pipeline is much more efficient. Many microcontrollers you also use lookup tables. Now it's time to go deep with an example, that is digital signal processor. Digital signal processors are used to stream data, and they are used to fetch multiple instructions at the same time using a specialized memory architecture and separate data and program memory. DSPs mathematically manipulate procedures, taking real-world aspects such as audio, video, voice, pressure, and digitize them. They are also used for performing mathematical operations like addition, subtraction, multiplication, and division. The processing of signals is essential because the information that they contain must be displayed and analyzed so that they can be converted to another signal to the format that users require that they find it interesting. So let's talk about the working of the digital signal processor. Analog to digital converters take the job of converting the above aspects, that is physical data or analog data, in terms of zeros and ones, that is digital signals. The DSP, that is digital signal processor, then digitize the signals and processes them. It takes the digitized signals and converts them to analog signals again using analog to digital converter, making it useful to the real world. The speed at which all these processes occur is really high. Let's see how the digital signal processor works on MP3 devices. It generally takes the inputs through receivers and converts them into a digital signal in the form of zeros and ones using analog digital converter. Post the conversion phase, encoding is performed and encoded file is thereby saved to memory. Next comes the decoding phase, where the file would be taken from memory, converted to analog signals using digital analog converter, and then the output is received through the speaker systems. This is the process that happens in the MP3 device. It also performs complex functions such as controlling volume, editing frequencies, and so on. A DPS can be used by the computer to control things such as efficiency, transmission, etc. Signals go through the processing phase first and then the transmission phase. Teleconferencing using telephone signals to transmit audio and video lines. The quality of signals could be manipulated or improved to appear better to the eyes of the user. It will be invisible to the eyes of the user. Example: echo cancellation on telephones. Although signals in the real world can be processed in analog way, these digitally processed signals can be transmitted with high speed and they are very much accurate. So let's discuss about the components of DSP. The components of digital signal processor are program memory. Now, it uses processed data and stores the program inside the memory. It is generally non-volatile. In this program memory, flash memory is used where reprogram is possibly using a hardware interface, and program memory generally uses the concept of stacked data memory. Data memory is called random access memory. It is a temporary place for storing variables and constants during program execution. The amount of memory, that is RAM, varies from one microcontroller to another compute engine. It performs mathematical operations and it collects data and programs from their respective places. It collects instructions from the program memory, and it also collects data from data memory. Input or output. The technique used to transfer data from an external device and a microcontroller called input output. The user communicates with the microcontroller through the input output. The users can enter their data through input device keyboard and collect their desired output from the external device printers or hard disk. These input or output devices are called peripherals, and they are most common devices that are used on microcontroller systems. Let's talk about the architecture of DSP. It has several components to it. One being software architecture. The instruction set used in DSP are irregular, while the common instruction sets are used in regular operations of a computer. DSP sets are used in specialized mathematical operations. Assembly programs are generally put into libraries for reuse. Instead, other machines use compiler methods to store essential algorithms. Many programs used in DSP are generally handwritten to facilitate easy programming. The data instructions include various operations such as arithmetic instructions, Boolean instructions, logical instructions, and flow instructions. Program flow consists of pipeline architecture and multiple accumulators. Next being hardware architecture. Hardware architecture consists of the physical components of systems. Generally, they provide the space for other systems to fit into the devices, and they also assess the other software components. They also provide room for the effective usage of software components. They combine with the various sectors of engineering to work together and develop new machines and architecture. However, we have to realize that hardware components cannot run properly with the help of software components. If we take modern aircraft for example, we have to use software embedded code to make it run efficiently. Memory architecture. Digital signal processors are generally used for running data, and they are specialized memory techniques to fetch data and instructions separately on different pathways. The concept of Harvard architecture is basically that, and data and instructions are fetched on the same bus as used in one human architecture. Memory at times use the cache storage to know about the delay operations. Next, the last being virtual memory. These generally do not use virtual memory as they rely on multitasking operations. Operations that use virtual memory generally use the concept switching, which is proven to increase latency. Okay, now as we have completed our depth brief about Harvard architecture using the example of digital signal processors, so let's come back to Harvard architecture and discuss its advantages. Since data and instructions are stored in separate buses, there are very few chances of corruption. Data that uses read-only mode and instructions which uses read-write mode are operated in the same way. They can also be accessed similarly. Generally, two memories would be present, one for data and other for instructions. They have different cell sizes, making use of the resources very effectively. The bandwidth that is used for memory is more predictable. They generally offer high performance as data and buses are kept in separate memory and travel on different buses. Parallel access to data and instructions can also be maintained. Scheduling would no longer be required as there are separate buses for data and instructions. Programmers can design the memory unit according to their requirements. Control unit gets data and instructions from one memory. Thus, it simplifies the architecture of the control unit. Disadvantages. The unoccupied data memory cannot be used by instructions, and the free instruction memory cannot be used by data. Memory dedicated to each unit has to be balanced carefully. The program cannot be written by the machine on its own as in one human architecture. Control unit takes more time to develop and is on the expensive side. There are two buses on the architecture, right? Which in the way means that the motherboard would be more complex, which in turn means there would be two RAMs and thus tend to have a very complex catchy design. That is the reason why it is used mostly inside the CPU and not outside of it, because it is very complex. Production of computer with two buses take more time to get manufactured and is again on the expensive side like the control unit. It has more pins on its ICs, therefore it is very difficult to implement it. These are the main disadvantages regarding Harvard architecture. So let's conclude about Harvard architecture machines. In terms of basics, it is present inside the CPU. Memory. Now it has separate memory for both data and instructions. The system on the memory can be accessed simultaneously. Instruction processing. In our architecture, instruction processing can be completed at a single phase if the pipelines are in appropriate places. Cost. Well, it's expensive. Uses. Many, and the prime example being digital signal processors. With this slide, I want to conclude this presentation, and guess I have successfully discussed about Harvard architecture machines, its advantages, disadvantages, and some unknown facts about them. Thank you for listening.